Eigenvalues and eigenvectors. CH Revant 21951 A66 A6. Hmm. Topics present in this slideshow are introduction, formal definition, overview, history, eigenvalues and eigenvectors of matrices, eigenvalues and the characteristic polynomial. Introduction. In linear algebra, a eigenvector or a characteristic vector of a linear transformation is a non-zero vector that changes at most by a scalar factor when that linear transformation is applied to it. The corresponding eigenvalue, often denoted by lambda, is the factor by which the eigenvector is scaled. Geometrically, uh, an eigenvector corresponding to a real non-zero eigenvalue points in a direction in which it is stretched by the transformation, and the eigenvalue is the factor by which it is stretched. If the eigenvalue is negative, the direction is reversed. Loosely speaking, in a multi-dimensional space, the eigenvector is not rotated. Formal definition. If T is a linear transformation from a vector space V over a field F into itself, and V is a non-zero vector in which V, then V is a eigenvector of T. If T of V is a scalar multiple of V, this can be written as T of V is equal to lambda V1, where lambda is a scalar in F known as the eigenvalue, characteristic value, or characteristic root associated with V. Here the form of T of V is equal to lambda V1. There is a direct correspondence between n by n square matrices and linear transformations from an n-dimensional vector space into itself, given any basis of vector space. Hence, in a finite dimensional vector space, it is equivalent to define eigenvalues and eigenvectors using either the language of the matrices or the language of the linear transformations. If V is finite dimensional, the above equation is equivalent to. Next, overview. Eigenvalues and eigenvectors feature prominently in the analysis of linear transformations. The prefix eigen is adopted from the German word eigen for proper characteristic own, originally used to study principal axis of rotational motion of rigid bodies. Eigenvalues and eigenvectors have a wide range of applications. For example, in stability analysis, vibration analysis, atomic orbitals, facial recognitions, and matrix diagonalization. In essence, an eigenvector V of a linear transformation T is a non-zero vector that, when T is applied to it, does not change direction applying to the eigenvector, only scales the eigenvector by the scalar value called an eigenvalue. This condition can be written as the equation T of V is equal to lambda V. The Mona Lisa example picture here provides a simple illustration. Each point on the painting can be represented as a vector pointing from the center of the painting to that point. The linear transformation in this example is called a shear mapping. Points in the top of are moved to the right and points in the bottom of are moved to the left, proportional to how far they are from the horizontal axis that goes through the middle of the painting. Here is a painting of the Mona Lisa. It is in the manner of a straight line. It is a manner of 90 degrees. It is manner of some mode to 90 degrees. The vectors pointing to each each point each point in the original image are therefore tilted right for left and made longer or shorter by the transformation. Points along the horizontal axis do not move at all when this transformation is applied. Therefore, any vector that points directly to the right or left with no vertical component is an eigenvector of the transformation because the mapping does not change its direction. Moreover, these eigenvalues all have an eigenvalue equal to 1 because the mapping does not change their length either. Linear transformations can be taken many different forms, mapping vectors in a variety of vector spaces. So the eigenvectors can be taken in many forms. For example, the linear transformation could be a differential operator, like in which case the eigenvectors are functions called eigenfunctions that are scaled by that differential operator, such as d by dx e power lambda x is equal to lambda e power lambda x. Alternatively, the linear transformation could take the form of an n by n matrix, in which case the eigenvectors are n by 1 matrices. If the linear transformation is expressed in the form of an n by n matrix A, then the eigenvalue equation for linear transformation above can be rewritten as the matrix multiplication AV is equal to lambda into V, where the eigenvector V is an n by 1 matrix. For a matrix, eigenvalues and eigenvectors can be used to decompose the matrix. For example, by diagonalizing it, eigenvalues and eigenvectors give rise to many closely related mathematical concepts. The prefix eigen is applied liberally when naming them. The set of eigenvectors of a linear transformation, each paired with its corresponding eigenvalue, is called the eigensystem of the transformation. Eigenvalues are often introduced in the context of linear algebra or matrix theory historically. However, they arose in the study of quadratic forms and differential equations. In the 18th century, Leonhard Euler studied the rotational motion of rigid body and discovered the importance of principal axis. Joseph Louis Lagrange realized that the principal axes are the eigenvectors of the inertia matrix. In early 19th century, Augustin Louis Cauchy saw how their work could be used to classify the quadratic surfaces and generalized it to the arbitrary dimensions. Later, Joseph Fourier used the work of Lagrange and Pierre-Simon Laplace to solve the heat equation by the separation of variables in his famous 1822 book Theory. Developed Fourier's ideas further and brought them to the attention of Cauchy. When combined them with his own ideas and arrived at the fact that real symmetric matrices have real eigenvalues. This was extended by Charles Hermite in 1855, to which are now called Hermitian matrices. Around the same time, Francisco Brisocchi proved that the eigenvalues of orthogonal matrices lie on the unit circle and found the corresponding result for skew symmetric matrices. Finally, Carl Carl Weierstrass clarified an important aspect in stability theory started by Laplace by realizing that defective matrices can cause instability. In real time, Joseph studied eigen value problems similar to the at the start of the 20th century. David Hilbert studied the eigenvalues of integral operators by viewing the vectors operators as infinite matrices. He was the first to use the German word eigen, which means own, to denote eigenvalues and eigenvectors in 1904. Though he may have been following a related usage by Hermann von Helmholtz for some time, the standard term in English was proper value, but the more distinctive term eigenvalue is the standard today. The first numerical algorithm for computing eigenvalues and eigenvectors appeared in 1929, which Richard von Mises published. The power method, one of the most popular methods today. The QR algorithm was proposed independently by John G. F. Francis. AV is equal to lambda V, where A is matrix, V and V is eigenvector, and lambda is eigenvalue. Eigenvalues and eigenvectors. Eigenvalues and eigenvectors are often introduced to students in the context of linear algebra courses focused on matrices. Furthermore, linear transformations over a finite dimensional vector space can be represented using matrices. Here is the eigenvalue and eigenvectors of matrices graph, where on x-axis lambda y and y is there, and on x-axis x and lambda x is there. Matrix A acts by stretching the vector x, not changing its direction, so x is an eigenvector of A. Consider n-dimensional vectors that are formed as a list of n scalars, such as the three-dimensional vectors x is equal to 1, minus 3, 4, and y is equal to minus 20, 60, minus 80. These vectors are said to be scalar multiples of each other, or parallel or collinear if there is a scalar lambda such that x is equal to lambda y. In this case, lambda is equal to minus 1 by 20. Eigenvalues and the characteristic polynomial equation as a non-zero solution V if and only if the determinant of the matrix A minus I is 0. Therefore, the eigenvalues of A are values of this upper cap that satisfy the equation. A minus lambda I is equal to 0. Using the Leibniz formula of determinants, the left hand side of the equation is a polynomial function of the variable lambda, and the degree of this polynomial is n. The fundamental theorem of algebra implies that the characteristic polynomial of n by n matrix, being a polynomial of degree n, can be factored into the product of n linear terms. A minus lambda I is equal to lambda 1 minus lambda into lambda 2 minus lambda, so on up to lambda n minus lambda.